Hello, I'm Clara Nellist and I'm a particle physicist. I work for the ATLAS experiment on the Large Hadron Collider at CERN, and I'm going to be doing a live Twitter chat for the Royal Institution. So I just wanted to give you a bit of background information about myself and the work that we do at CERN, so that when it comes to the chat you can ask me lots of questions on everything you want to know about the LHC and specifically what's going to happen in the future. So my research is split into two parts. I work on pixel detectors for the upgrade of the ATLAS detector, and these are a bit like the sensors in your digital camera. I also work on the Higgs boson and specifically how it changes into tau particles, which are the heavier cousins of electrons. And this is the most direct way of measuring the Higgs boson interacting with ordinary matter. When we discovered the Higgs boson at CERN, we didn't directly measure it. What we did is measure the particles that it very quickly changed into. So the type of particle, their mass, the direction that they're going in. This all gives us information about the original particle that they came from. And you can think of this like a fingerprint. So the Higgs boson has many different fingerprints, so different particles it can change into. And what we want to know is how often it changes into these particles. And this gives us information about its properties. So ATLAS itself is a general purpose detector. This means that it aims to measure everything that passes through it. It's in different layers, so like an onion, and mainly in three sections. So at the very heart of ATLAS we have the tracker, and the job of the tracker is to measure charged particles as they pass through, and specifically their path. And so we have a magnet which bends these charged particles, which also gives us information about their mass or their momentum. After this we have the calorimeters, and this measures the energy of the particles, and it does this by stopping them. So when they give up their energy, then we can measure it. And after these two sections we only have two types of particles left. So one type are the neutrinos, and so these actually don't interact with our detector at all. So we have to infer that they were there from looking at the other particles that were created. And the second type of particles are muons, and the muons travel all the way out, and we have a specific section just for them called the muon chambers. ATLAS has a sibling experiment called CMS, and this was built by an entirely different group of engineers and physicists. And the reason that there are two general purpose detectors on the LHC is that if one of them made a discovery and the other didn't, then this would raise a lot of questions. We also have the LHCb experiment, which is looking at the difference between matter and antimatter. And we have ALICE that looks at when we collide lead ions together at the LHC. And this is to understand the very early universe. The LHC and the experiments have been switched off for the last year and a half, but that doesn't mean that we've been on holiday the whole time. What we've done is we set aside this period of time to allow repairs and upgrades of the accelerator and the experiments to be made. So for example, the LHC has been mending connections in the magnets to make sure that they're all perfect. And also the ATLAS detector, for example, has installed a new layer of pixel devices right at the very heart of the ATLAS detector. And this will improve measurements of tracks through our detector, which is great for the identification of, for example, B quarks. So there's a lot to keep us busy in the next few years when we switch the LHC back on. We want to do precision measurements of the Higgs boson to understand if it's really the one that's predicted by our model. We also want to study matter and antimatter in great detail to understand why our universe is matter dominated. There's also the search for supersymmetric particles, which could be a candidate for dark matter. And there's always the possibility that we'll discover something completely unexpected, and that's what's really exciting. So hopefully that's given you a bit of background about me and some of the work happening at CERN. There's loads more to talk about, so if you come on Twitter and if you have any questions, just let me know. Thanks!